Hi everyone, how's it going? Welcome back to another video in our digital system series. This is the first video in a sequence where we'll focus entirely on Boolean algebra. If you're in college and you're struggling with the subject, and if you're studying electrical engineering, computer engineering, or any related field, then these videos are perfect for you. So why is Boolean algebra important? Boolean algebra is essential because it forms the foundation of digital logic. Every digital electronic system, like computers, calculators, smartphones, microcontrollers, and even simple circuits like alarms or traffic lights, relies on Boolean logic to operate. Boolean algebra is used to design logic circuits, optimize digital systems, understand how digital devices work, and create decision-based logic for programming and control systems. It's also deeply related to microcontrollers, control systems, and low-level programming languages such as assembly and C. In this first video, we're going to focus on Boolean operations and Boolean expressions. So before we get started, if you haven't watched the previous lesson on the different ways to represent logic functions, I recommend checking it out. It will help you get the most out of today's topic, where we start working with Boolean expressions using Boolean algebra. To continue, we first need to clarify three fundamental terms in Boolean algebra: variable, complement, and literal. Let's go through each one. A variable is usually represented by an uppercase letter, and that letter represents a logic value, either 0 or 1. For example, the variable a can take 0 or 1. Here's an important detail to avoid confusion. A variable represents a logic value and not a numerical value. As I mentioned in the first video of this playlist, numerical value represents quantity. Logic value represents a state. In digital electronics, a logic state can represent false and true, off, on, low level, high level, absence or presence of voltage or current, and so on. A simple analogy, think of a lamp. Lamp off, logic 0. Lamp on, logic 1. Another key point is a variable cannot take both values at the same time. It cannot be 0 and 1 simultaneously. Just like a lamp cannot be on and off at the same time, and a door cannot be open and closed at the same time. You can think of a variable as a small box. You can put either 0 inside or 1, but not both. A complement is simply the inverse of a variable, and the way we represent it is by placing a bar over the variable indicating that it is negated. You'll see me use this all the time. A bar, a negated, not a, the inverse of a. All these terms mean exactly the same thing. The idea is very simple. If a normal variable equals 1, its complement equals 0. And if a normal variable equals 0, its complement equals 1. In other words, the variable always represents the opposite state of the original variable. To make this even more intuitive, let's think of everyday examples. If a door is open, its complement would be the door open. If a lamp is on, its complement would be lamp off. In the same way, in digital logic, a normal variable represents one state, its complement represents the opposite state. That is, A represents one state, A bar represents the opposite state. Okay? In summary, the complement is simply the inverse logical value of a variable. And finally, literal. A literal is simply a variable in either its normal form or its complemented form. This means if we have the variable a, then a is a literal. If we have its complement, that is a bar or a negated, then a negated is also a literal. Both are literals. It doesn't matter whether the variable is negated or not. Any variable a, b, c, or its complement, a bar, b bar, c bar, is considered a literal. Let's look at some examples. A plus b, sum of two literals. A times b times c negated, multiplication of literals. Notice that c negated is also a literal. B bar or b negated plus c. Another example with two literals. The key idea is a literal is the simplest form of a variable inside a Boolean expression. It can appear in its normal form or complemented form, as you can see in the examples already mentioned. Both are treated as fundamental elements of logic operations. In summary, a literal is any single variable, either in its normal form or complemented form. Are these terms clear now? If there's anything you didn't fully understand, go back to that part of the video and watch it again. And if you still have questions, feel free to leave them in the comments. I'll do my best to answer them as soon as I can. It's really important that you don't move on until you understand each step I'm explaining here. Now, let's start talking about logic operations. The first is Boolean addition, or logic OR operation. Boolean addition follows this pattern. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. And 1 plus 1 equals 1. And you might ask, man, how can 1 plus 1 be equal to 1? This is where you must be careful and understand something very important. A logic operation is not the same as an arithmetic operation. They are completely different ideas. In decimal system, of course, 1 plus 1 equals 2. In binary number, the number 2 is written as 1, 0. But in Boolean algebra, we are not adding quantities. We are working with logic states. And these operations are performed by logic gates. In the first video of this playlist, I explained how logic gates work. Here, we'll quickly reinforce that concept. So why 0 plus 0 equals 0? Because these operations are performed by the OR gate. And the easiest way to understand this is to use an analogy with an electrical circuit in parallel. We have a voltage source here, two switches connected in parallel, A and B, and the light bulb. The switches represent the inputs of the OR gate. The light bulb represents the output. The idea is switch off, logic 0, switch on, logic 1. Now let's analyze the case 0 plus 0, that is, switch A off and switch B also off. If current comes from the voltage source, it has two possible paths. But since both switches are off, the current cannot flow. Result, light bulb off, that is, logic 0. And that's exactly why in Boolean operation, 0 plus 0 equals 0. This analogy helps you visualize how the OR gate behaves and understand what is that is operated are logic state and not numeric values. Now that you understand how the OR gate behaves in the case 0 plus 0, the remaining patterns become much easier to interpret. Let's see, 0 plus 1 equals 1. Here, one input is 1, meaning one of the switches is on. Since the current has at least one available path, the lamp turns on, and the output is 1. That is, the result is 1. Okay? Let's see the case 1 plus 0 equals 1. This is the same idea as before, just reversed. Because one path is still available, the lamp turns on. That is, output 1. And finally, 1 plus 1 equals 1. With both inputs equals to 1, both switches are on. Naturally, the lamp receives current and stays on. So the output is 1. So in Boolean OR operation, the output is 1 whenever at least one input is 1. The output is 0 only when both inputs are 0. This completes the core idea of Boolean addition. Now let's solve a simple exercise to make everything is clear. Determine the values of A, B, C, and D to make the sum term A plus B negated plus C plus D negated equal to 0. This is a sum term, that is a Boolean OR expression. So remember the key rule. An OR expression outputs 0 only when all inputs are 0. So our goal is to make every input of this OR operation equal to 0. Step 1. Let's understand each term. Look at the expression again. We have the variable A in its normal form, B in its complemented form, that is B negated, C in its normal form, and D in its complemented form. Since the output must be 0, all these must be 0 at the same time. So step 2, determine the required values. To make each term equal to 0, A and C must be 0, like this. To make the complemented variable equal 0, initially B and D must be 1, okay? Like this. So the values that satisfy the condition are A equals 0, B equals 1, C equals 0, and D equals 1. If you look at the expression, A will remain 0, B initially equals 1, will turn 0, C will remain 0, and D negated will become 0, like this. Okay? Alright, 0 plus 0 equals 0, 0 plus 0 equals 0, and 0 plus 0 equals 0. So the result is 0. So in an OR expression, the only way to get 0 if every input is 0. So you assign the values in a way that forces each term to become 0. For complemented variables, you must assign the opposite value. Now let's talk about Boolean multiplication, also called AND operation. Boolean AND follows this fundamental rule. 0 times 0 equals 0. 0 times 1 equals 0. 1 times 0 equals 0. And 1 times 1 equals 1. But remember, this is not an arithmetic multiplication. This is a logical operation performed by the AND gate. To understand it in the simplest way, let's use the same electrical analogy we used earlier. But now the switches connected in series. Imagine a very simple circuit. A voltage source, two switches connected in series representing the input of the AND gate, and the lamp at the end of the line. Let's use the same idea. Switch off, logic 0. Switch on, logic 1. Just like in a real AND gate, the lamp will turn on if all switches are on. So let's analyze the first case. 0 times 0 equals 0. That is switch A off and switch B also off. The current tries to flow, but the first switch is off, so the lamp never turns on. So the output is 0. And that's why 0 times 0 equals 0. Next case, 0 times 1 equals 0. Let's visualize the circuit. Even though B is on, A is off. The current cannot pass through the first switch. Results, output 0. That is lamp off. Next case, 1 times 0. That is switch A on, switch B off. The current passes to the first switch, but it gets blocked at the second switch. So lamp off, that is output 0. Finally, 1 times 1 equals 1. That is switch A on and switch B on. Now the path is completely free. The current flows through both switches and reaches the lamp. That is output 1. And that's why the AND gate produces 1 only when all inputs are 1. If any other scenario, the lamp stays off. That is, the output is 0. Summary, why the AND operation works this way. Boolean multiplication checks if all conditions are true at the same time. The series switch analogy makes this intuitive. If any switch is off, the current can't flow. Only when every switch is on does the lamp light up. So let's solve another exercise. Determine the values of A, B, C, and D that make the product term A times B negated times C times D negated equal to 1. If the literal A and C are normal, its value must be 1, like this. If B and D are in their complemented form, the original variable that is B and D must be 0, so that after negation, it becomes 1. Applying this to the term A times B negated times C times D negated, that is A normal, B complemented, C normal, and D complemented. These logic values satisfy the condition. So A remains 1, C remains 1. B negated and D negated will not remain 0, like this. Alright, 1 times 1 times 1 times 1 equals to 1. Just remember the electric circuit with switches connected in series. In this case, the circuit has 4 switches connected in series. That is, each switches must be on for the lamp light up. And that's it for today's lesson. I hope this video helped you clearly understand how Boolean addition and Boolean multiplication work, and how we interpret these operations through logical reasoning and switch-based circuits. If something wasn't completely clear, don't worry. Take your time. Everyone has their own learning pace. If you still have questions, feel free to leave them in the comments. I'll be happy to help you as soon as I can. If this lesson was useful for you, don't forget to give the video a like and subscribe to the channel so you don't miss the next lessons. In the upcoming videos, we'll continue our study of Boolean algebra, diving deeper into Boolean expressions. Thank you so much for watching, and I'll see you in the next video.